Instant coffee starts as bold roasted beans transformed into a powder that melts in seconds. Inside the factory, heat and pressure turn fresh brews into crisp, aromatic granules. Today, we uncover the high-speed process that turns a simple bean into instant energy in your cup. On vast plantations near the equator, coffee trees grow in neat, endless rows that sway in warm winds, their leaves glossy under the sun. The air smells faintly of earth and sweetness, and the red coffee cherries glint among the green like hidden jewels. Inside each cherry are 2 seeds, the coffee beans themselves. And it's these tiny seeds that will eventually be transformed into the brown, aromatic crystals that dissolve instantly in hot water. Harvesting is the first decisive step, and it's not as simple as it might seem. The timing has to be perfect. If the cherries are picked too early, the beans inside will be grassy and acidic. Too late, and they'll be dull or fermented. Some farms rely on hand picking, where skilled workers move along the rows and pluck only the ripest cherries, their baskets filling slowly over the day. Others use machines that shake the trees just enough to loosen mature fruit while leaving the rest intact. Once collected, the cherries begin to ferment almost immediately, so they must be processed within hours. Washed, pulped, and spread out to dry under the open sky, or in mechanical dryers that blow warm air across the beans until their moisture drops to about 12%. At this stage, the beans are pale green, hard, and far from aromatic. They smell grassy, not roasted, and they're still covered in a thin, papery skin called parchment. Once removed, the beans are graded and sorted. Optical sensors check for color consistency, while air jets remove lighter impurities like husk or dust. It's astonishing how much attention is paid before the real transformation even begins. The coffee destined for instant products usually comes from Robusta or blended varieties, chosen for their strong flavor and high caffeine content, though some factories mix in Arabica for a smoother profile. These raw beans are then shipped in enormous containers to processing plants. When they arrive, they enter a world of polished steel, heat, and carefully timed automation. The first major operation is roasting, and this is where the green beans become the coffee we recognize. In a factory, roasting isn't done in small drums like at an artisan cafe. Instead, it happens in vast, continuous roasters that can handle hundreds of kilograms per cycle. Inside these machines, hot air circulates at temperatures between 200 and 250 degrees Celsius, gently turning the beans as they darken and expand. During roasting, hundreds of chemical reactions take place: caramelization of sugars, breakdown of acids, and the famous Maillard reaction, which produces the deep, brown color and the complex aroma. The beans crack audibly as internal moisture and gases expand, a sound like faint popcorn popping. The air fills with a rich, smoky smell that's both bitter and sweet, carrying notes of chocolate, toasted nuts, and spice. Sensors monitor every variable, temperature, humidity, even the reflectivity of the beans, to ensure perfect uniformity. Too light a roast, and the flavor will be thin. Too dark, and it turns harsh. When the beans reach their target profile, they're cooled almost instantly with powerful air jets. This sudden cooling, called quenching, halts the roasting process immediately. Without it, the residual heat would continue cooking the beans, distorting their flavor. The freshly roasted beans emerge warm to the touch, oily and intensely aromatic. Standing near a cooling tray in such a plant is unforgettable. The smell alone could fill an entire warehouse. Next comes grinding. The roasted beans are brittle now, and they're fed into industrial grinders that crush them to a carefully controlled particle size. The grind is crucial. Too fine, and extraction becomes muddy and overdone. Too coarse, and the coffee loses strength. Factories use multiple stages of grinding, passing the coffee through rollers that steadily reduce it to uniform granules. The goal isn't to make powder yet, but to prepare it for extraction. the step that essentially brews the coffee on an enormous scale. Extraction takes place in tall, stainless steel columns that can rise several stories high. Imagine a giant version of a French press operating under precise heat and pressure. Hot water, usually around 150 to 180 degrees Celsius, is pumped through the columns under pressure, allowing it to extract soluble compounds from the coffee quickly and efficiently. The process happens in stages. The first columns capture delicate aromas and acids. The later ones draw out stronger, more bitter flavors and solids. Technicians monitor the strength of the extract as it flows through, adjusting the ratio of stages to achieve a balanced, full-bodied flavor. What comes out at the end of this step isn't a drinkable beverage. It's a thick, dark syrup, many times more concentrated than brewed coffee. It looks almost like molasses and smells intensely roasted. The challenge now is to turn that syrup into something solid, something that can dissolve back into liquid form later without losing the original aroma or taste. Before drying, the extract is filtered to remove insoluble particles and oils that could cause clumping or uneven texture. Some factories even distill the coffee vapors released during extraction, capturing volatile aromatic compounds that might otherwise be lost. These are stored separately and later reintroduced to the powder to enhance flavor. Every fraction of aroma matters. The goal is to retain as much of the fresh brewed character as possible. Now comes one of the most fascinating parts of the entire process: drying the extract into powder. There are two main methods used in the industry: spray drying and freeze drying, each producing a distinct kind of instant coffee crystal. Spray drying is the faster, more economical option. The coffee extract is sprayed through fine nozzles into a towering chamber filled with hot air. The droplets, suspended mid-air, dry almost instantly as they fall, turning into tiny hollow spheres of coffee powder before they even reach the bottom. The air smells warm and toasted, and inside the chamber, it looks like a golden brown mist of particles drifting down in slow motion. By the time the powder hits the collection floor, it's completely dry, light, crisp, and ready to dissolve in water. The temperature must be carefully controlled to avoid burning the powder or driving off too much aroma. Some factories re-inject the previously captured aromatic compounds at this stage, gently coating the powder as it cools, giving it that fresh coffee scent when the jar is opened. Freeze drying, on the other hand, is slower and more delicate, often reserved for premium instant coffees. In this method, the extract is first cooled into a slushy concentrate and then frozen solid at extremely low temperatures. The frozen slabs are broken into small pieces and placed in vacuum chambers, where the ice is removed through sublimation. It turns directly from solid to vapor without melting. What's left behind is a porous, crystalline structure that preserves both flavor and aroma remarkably well. These crystals have a satisfying texture and a rich color, and they dissolve beautifully in hot water, recreating a more authentic coffee experience. Both methods require immense energy and precision. The machinery involved looks like something out of a chemical plant. Huge dryers, insulated vacuum vessels, intricate networks of pipes and valves. The roar of air compressors and the hum of pumps fill the background constantly. Despite the industrial scale, every step is about preserving the soul of the coffee bean, the delicate aromatic balance that defines the beverage. Once the drying is complete and the coffee has taken on its familiar granular form, the next stage focuses on perfecting its texture and appearance. Because raw dried coffee powder, whether spray dried or freeze dried, can sometimes be too fine or irregular, leading to clumping, uneven dissolving, or a dusty appearance that doesn't feel right when poured into a cup. To solve this, factories use a process called agglomeration, a word that sounds technical but describes something quite intuitive. It's the gentle binding together of the fine particles into slightly larger, more uniform granules, each with a porous structure that allows water to rush in and dissolve them instantly. In a large stainless steel chamber that hums with quiet, steady vibration, the fine coffee powder is sprayed once again with a controlled mist of steam or warm water. The moisture causes the tiny particles to stick together just enough to form clusters, which then tumble in a rotating drum. As they move, warm air circulates around them, drying the clusters once more and locking them into place. The result is a grain that looks a bit like brown sugar. Irregular, yet cohesive, sturdy enough to resist dusting, but still fragile enough to melt away the instant it meets hot water. Workers and sensors constantly monitor the particle size and density because both affect not just how the coffee dissolves, but how it looks and feels when it hits the spoon. A slightly darker hue or a subtle sheen can change consumer perception entirely, so the factory's control room pays close attention to every detail. Once the texture is perfected, the granules are cooled and transferred through sealed pipes towards the packaging lines. At this point, the air in the plant is thick with roasted aroma. Even from a distance, it smells like an enormous cafe. The coffee, however, is vulnerable. Those delicate aromatic molecules that give it depth can easily evaporate or be degraded by exposure to oxygen or moisture. To preserve them, factories maintain strict environmental controls. The rooms are cool, dry, and filled with filtered air. Humidity levels are tightly regulated. In some sections, nitrogen is pumped into the air system to push out oxygen altogether, creating an inert atmosphere that keeps the product fresh. Before packaging begins, samples are taken from every batch and sent to the quality control lab. There, technicians test the granules for moisture content, solubility rate, color uniformity, and flavor intensity. Small brews are made using carefully measured water at specific temperatures, and trained tasters evaluate aroma, body, and aftertaste. Instant coffee might appear simple, but each brand has a signature profile that must be reproduced consistently. That warm nuttiness, that faint hint of chocolate, that gentle bitterness that feels coffee-like without being overwhelming. Consistency is everything, and even a minor variation in roast or extraction can shift the flavor away from the standard. When the batch is approved, it moves along a system of conveyor belts that lead to the filling machines. These machines are wonders of precision engineering. Tall, multi-nozzle dispensers that can fill hundreds of jars or sachets per minute without spilling a single grain. Glass jars, plastic containers, or foil pouches arrive from another line, cleaned and sterilized with blasts of filtered air or ultraviolet light. The filling system measures exact weights with digital accuracy, sometimes adjusting in real time as sensors detect minute fluctuations in density. The gentle hiss of nitrogen fills the headspace of each container before sealing, a protective cushion that prevents oxidation and keeps the coffee's aroma intact for months, even years. Meanwhile, the caps are screwed on and labels applied by robotic arms that work in perfect rhythm. The printed labels are vivid and glossy, carrying information about roast strength, serving suggestions, and sometimes an image of steaming coffee that seems to rise off the surface. Beneath all that marketing lies an astonishing choreography of mechanical precision. Each jar is scanned for correct fill level and seal integrity. Any container that doesn't meet the standard, even slightly, is automatically diverted off the line with a gentle push of air. Nothing is left to chance. As the packaged jars move toward the end of the line, they pass through metal detectors and X-ray scanners to ensure no foreign material has found its way inside. The instant coffee industry runs under strict food safety standards. Cleanliness is absolute. Workers on the floor wear hairnets, gloves, and anti-static coats. Shoes pass through disinfectant baths. The noise level is high. The hiss of air jets, the hum of conveyors, the whir of vacuum pumps. But there's a sense of calm precision in the movement, like watching a perfectly timed dance. The filled jars are packed into cardboard trays, shrink-wrapped in plastic film, and palletized by automated stacking machines that build tall, stable towers of product, ready for shipment. Forklifts glide between the aisles, guided by sensors that follow magnetic strips embedded in the floor. The entire process is digitized. A central control system tracks each batch from roasting to packaging, logging temperature readings, weight data, and timestamps in real time. In modern facilities, there's almost as much computing power as mechanical energy. Beyond the factory floor, in climate-controlled warehouses, these pallets wait to be distributed to markets around the world. The smell of roasted coffee hangs faintly even here, absorbed into the air and cardboard. Depending on destination, the coffee might travel by truck, by ship, or even by rail, stored in sealed containers that protect it from humidity and temperature changes. The logistics side of instant coffee is as intricate as its manufacturing. Global networks of suppliers, packaging plants, and distributors ensuring that a jar made in one corner of the world can sit on a supermarket shelf thousands of kilometers away, ready to meet its moment with a kettle and a mug. But inside every jar, the coffee is sleeping, waiting for heat to bring it back to life. Those tiny granules, though seemingly dry and inert, are full of preserved aroma molecules and flavor compounds frozen in place by science. When hot water touches them, the reaction is almost immediate. The crystals dissolve, releasing steam that smells like a cafe on a rainy morning. This is the miracle of solubility, engineered through careful control of drying and granule structure, the culmination of every step that came before. Behind the simplicity of that moment lies a staggering amount of engineering. The spray drying towers that create powdery clouds of coffee are as tall as apartment buildings. The vacuum systems that handle freeze drying can maintain temperatures below -40 degrees Celsius while sucking vapor out of solid ice. The extraction systems operate under pressures strong enough to drive water through steel filters dozens of times a day without faltering. Even the simplest factory is a miniature city of pipes, valves, sensors, and conveyor belts, all humming together in quiet synchrony. And yet, for all that machinery, the process still feels profoundly human. It's built on centuries of coffee culture, from Ethiopian highlands to European cafes, refined through the language of chemistry and industrial design. The people who run the machines, who check the gauges and test the samples, are caretakers of that heritage. They make sure that what ends up in the jar still carries the warmth and familiarity of the drink that started it all. The scale is almost difficult to grasp. A single large plant can produce tens of tons of instant coffee per day, enough to fill millions of cups. The waste heat from one roasting unit might be reused to preheat incoming air for another, part of an elaborate energy recovery system designed to make the process more sustainable. Water used in extraction is filtered and recycled through closed-loop circuits. Even the coffee aroma captured during processing is collected, condensed, and reincorporated rather than vented away. Nothing is wasted if it can be saved, because every molecule of flavor has value. And somewhere near the end of the line, where finished jars roll past in an endless stream, there's usually a point where an operator stands, lifting one at random, twisting the cap, and taking in that first whiff. A rich, roasted scent that's the signature of success. In that instant, the long journey from green bean to golden crystal comes full circle. The machines might have done the heavy lifting, but the decision to approve that scent, that balance, that recognizable note of coffee, rests with a human sense of smell trained over years. Inside the instant coffee factory, even after the product is packaged and ready for shipment, the operation never really stops, because every hour of every day, there are systems quietly running in the background to ensure the entire process stays consistent, efficient, and safe. The heart of this invisible network is a combination of sensors and data systems that record everything, from the temperature of roasting air to the humidity levels in the storage rooms. and this real-time monitoring allows engineers to trace every jar of coffee back through its entire production history, identifying which batch of beans it came from, which roaster handled it, and which extraction columns brewed it, creating a traceability map so detailed that if a single inconsistency appears, they can pinpoint the exact moment it occurred. This kind of control is essential because instant coffee is a product that lives or dies on uniformity. Consumers expect it to taste exactly the same, whether they open a jar in Tokyo, Sao Paulo, or Berlin. And achieving that requires not only advanced technology, but also a deep understanding of chemistry and sensory behavior. Inside the quality labs, analysts don't just taste the coffee. They study it at a molecular level, using gas chromatography to measure volatile compounds, spectrometers to check color values, and precise moisture analyzers to confirm stability. The goal is to ensure that each crystal has the same composition of sugars, acids, and aromatic oils, all locked in place and protected from oxidation by the drying process. The science of aroma is one of the most challenging parts of coffee manufacturing. The smell of coffee, that complex mix of hundreds of volatile molecules, is fragile. Many of those molecules begin breaking down the moment they're exposed to air. During extraction, factories often capture these vapors by condensing them into a cold liquid, known as coffee aroma concentrate. Stored at sub-zero temperatures, this concentrate is later sprayed onto the dried granules just before packaging, reintroducing the very aromas that might have been lost earlier. The process requires split-second timing. If the vapor is captured too early or too late, the balance of notes, smoky, fruity, caramel-like, will shift. The aroma concentrate is like the perfume of coffee, distilled from its own breath, and returning it to the granules gives the final product a smell that feels fresh and familiar when the jar is opened. Energy management is another hidden marvel of instant coffee production. The entire process, from roasting to freeze-drying, consumes huge amounts of heat and power, and modern plants are designed like closed ecosystems to minimize waste. The hot air that leaves the roasting drums doesn't simply vanish into the atmosphere. It's filtered, cooled, and redirected through heat exchangers that warm up incoming air for the next roast. Water used during extraction is cleaned, filtered, and reused in a cycle that reduces both waste and cost. In some facilities, the biomass from coffee husks and spent grounds is burned in boilers that generate steam to power the plant, turning what would have been waste into renewable fuel. The hum of machinery and the rhythm of conveyor belts mask this elegant web of resource efficiency, a quiet ballet of physics and sustainability that keeps the process balanced. The freeze-drying units are perhaps the most impressive machines in the entire operation. Enormous metal chambers that look like futuristic capsules. Inside, the temperature drops to extremes, pues sometimes below -40 degrees Celsius, while powerful vacuum pumps lower the pressure so that ice crystals inside the frozen coffee slabs sublimate directly into vapor. This process can take several hours, sometimes an entire day, as the ice disappears without ever melting. Technicians peer through small circular windows, watching as the color of the slabs slowly changes from dull brown to a lighter, matte texture, signaling that the drying is complete. What remains is a delicate matrix of porous granules, each one preserving the flavor compounds with remarkable precision. When handled, they feel slightly brittle, almost airy, as though holding concentrated fragrance in solid form. Once these granules are collected, they're sieved to remove dust and uniformize the size before heading toward agglomeration and packaging. And every movement from this point on happens in sealed pipes that keep oxygen out. Even the lighting in some areas is carefully chosen because ultraviolet light can degrade certain aromatic molecules. The air smells faintly roasted everywhere, even after multiple filtration systems, a constant reminder of the product's potency. It's said that workers in such plants often lose sensitivity to the smell of coffee after years of exposure, yet visitors are usually overwhelmed within minutes, their senses flooded by the richness of it. Beyond the production floor, there's another world, the research and development labs, where food scientists and flavor engineers work on improving the product. Instant coffee might seem like a finished invention, but innovation never stops. In one corner, a group might be experimenting with microencapsulation, a technique that traps volatile coffee oils inside tiny edible shells to protect them from oxygen and light. In another, chemists test new drying parameters that could preserve more delicate floral notes, often lost in high heat drying. Some teams work on decaffeination methods that maintain full flavor without bitterness, while others study how small variations in grind size can change extraction efficiency by fractions of a percent, which when scaled up could mean tons of coffee saved each year. Every discovery is documented, tested, and often fed back into production lines gradually, each improvement folded seamlessly into the next batch. On the sensory side, professional tasters known as cuppers hold daily sessions. They sit before long tables lined with identical cups of reconstituted instant coffee, each brewed under strictly identical conditions. Same temperature, same water to powder ratio, same stir time. The room is silent except for the sound of spoons dipping, liquid slurped noisily across the tongue, and quiet scribbling of notes. The tasters look for texture, clarity, and aroma retention, and they can detect subtle shifts invisible to instruments: a slightly flatter finish, a hint of extra acidity, an aroma that lingers half a second longer than it should. Their job is part science, part art, and their feedback shapes future production adjustments. In many factories, the sensory evaluation area sits right next to the control room, allowing technicians to tweak variables in real time. If a batch shows faintly over-roasted notes, the roasting temperature curve can be adjusted immediately for the next run. If solubility seems too slow, the granule size distribution might be recalibrated. Every decision is made quickly, and the data from each change is stored digitally, forming part of the plant's memory, a living database of taste. Meanwhile, the packaging systems continue their ceaseless rhythm. Jars clink softly as they move on stainless steel conveyors, the labels spinning onto their surfaces with perfect alignment. Some lines fill small, single-serve sachets, thin packets that must be precisely sealed to prevent moisture intrusion. The machines run at astonishing speed, cutting, filling, and sealing hundreds of sachets per minute in a blur of movement. The air around them is cooler, drier, and filtered to near sterility. Even the human workers enter through air showers that blow away lint and dust. Inside this space, the focus on cleanliness borders on surgical. In warehouses, towering stacks of packaged coffee sit under steady air circulation, waiting for distribution. The logistics systems coordinate shipments so that stock rotates continuously, with the freshest product always moving first. Each pallet is barcoded, each shipment traceable through digital ledgers that connect to retail distribution centers worldwide. From there, the jars and packets disperse into the world, into cafes, hotel minibars, office pantries, and supermarket shelves, carrying within them the work of hundreds of people and the quiet power of thousands of machines. When all these layers of complexity finally meet a single act, a spoon dipping into a jar, granules tumbling into a cup, and hot water poured over them, the speed of transformation hides the depth behind it. The granules fizz slightly as they dissolve, a faint hiss rising before the aroma blooms. It's a moment that lasts only seconds, but it's built upon weeks of engineering, months of harvest, and years of refinement. Every sip connects back to that long, precise chain of creation, from the green slopes where the coffee grew to the cold, vacuum chambers where it was crystallized. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as overconching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, They are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, The peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, The mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 bricks. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel's structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms or high-speed diverters organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data embedded in barcodes or RFID tags about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars' global standardization team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from over-processing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, A rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough-making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sourced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, Both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter. The fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact.